Okay, so I start from here. Once we have learned the basic operations using the matrix tensor and its reciprocal, we are ready to define covariant, contravariant, and mixed arrays properly. For this, we introduce two curvilinear systems, xi and x bar I. The system xi, being curvilinear, is a temporary notation. We will make it Cartesian again afterward if an array vi in the xi system transforms into v bar I according to the rule. Okay. So this is like, see, j is up, summation. This is I downstairs. So because the I is in downstairs, so you have downstairs, vi. So then contravariant case, this is very complicated. Oops. J is here, this is a mistake. I think it's typo. So J has to be downstairs and summation always go with x, not x bar. This is x. I part is not non-summation, not summed. This is x bar. So here same. Summation part is x. And downstairs here we have non-sum. Non-sum is x bar. See? Here non-sum is upstairs. Non-sum, so that's why we have upstairs. Yeah, so it's a little bit. The rule is very systematic. We write it with a superscript as this. Note that the coordinate differentials themselves transform as. So this transform like V. So we have bar, so you have bar upstairs, which is a rule for contravariant arrays. This is a reason contravariant arrays. This is the reason for using superscripts for coordinates. I don't understand. What is the reason? Not clear. This is the reason. What? What is the reason? Consider the partial derivatives of scalar function. we find that they follow the covariant rule. Yeah, covariant rule. As we discussed in the last chapter, geometry or physical considerations determine the tensor nature of a given array. We may extend the preceding rules to second or higher rank tensors. For example, covariant tensor, we go like this is downstairs subscript indices, and upstairs you have summation, and summation part is x. Contravariant, you have summation part downstairs, then x bar upstairs. You have mixed tensor AMN. So M1 you go summation downstairs, M1, N1 summation upstairs. Okay. In Cartesian coordinates, the base vector EI can be used to construct reciprocal base vector EI. Because of their orthonormality, we end up with EI up equal EI down. Thus, subscripted quantities and corresponding superscripted quantities are identical, or there is no need to distinguish covariant components from contravariant components. We have already used this idea when we referred to delta ij, Kronecker delta ij, and eijk. Another convention consistently used in general tensor analysis is that the summation convention applies when the repeated pair of indices occurs in subscript-superscript form. That is, we should write the distance formula as this. So K and K are summation convention. I and J are summation convention. Physical components. As mentioned earlier, in general tensor analysis, the base vectors may not be unit vectors, nor may they have the same dimensions. However, we may convert them to unit vectors by dividing them by their magnitude. For example, the relation V equals Vi up Gi can be written as V equals Vi square root G11 G1 divided by square root G11 plus blah blah blah. From this, we can extract the physical component V1 What is this is a question, right? What is G11? What is G11? Very strange. Then he says this equal this to be V1. Similarly, for the covariant components in this way, the physical components are of the form V1 downstairs is V1 square root G11 upstairs. Is it not so clear? I think the explanation is not sufficient. Okay, it's not clear. Not clear. Don't worry. This is not clear. Don't worry. Okay, so next I will go do chapter 3.3. This one I will go next. I will do next.